Okay. Hello, everyone. So today we're going to discuss carbohydrates and glycosaminoglycans and glycoproteins. I know this word is so long and it looks really scary, but overall, inshallah, this lecture is not going to be as intimidating as it is. Okay. And I got you a bunch of candy, guys, because we're talking about carbohydrates. Anyways, before I go into the lecture, if you guys have any question, please type it in the chat or feel free to unmute yourself and to speak out loud. I would love to answer your questions like at the spot, just so that you don't get confused, because I want you guys to like understand everything. Okay? Yalla, let's start. Okay, so carbohydrates. What are carbohydrates? Carbohydrates, if you guys think like when I tell you carbohydrates, what's the first thing you think of? Probably like bread, sweets, so on. So carbohydrates, usually they include sugars, all right? And not like by sugar, we can either mean monosaccharide or polysaccharides. Monosaccharide means one single sugar, all right? From the name mono, one. It's the simplest carbohydrate that ever exists, all right? And we can also have something called polysaccharides. And from the name poly, which means it's composed of a lot of single sugars, all right? So monosaccharides, wait, okay. So monosaccharides, they have the formula that you can see in here, CH2ON. So basically, depending on how many carbs, so basically the basic formula of a carbohydrate is CH2O. All right. So let's say we have 6 carbons in whatever, like in like glucose. All right. So what do? You just multiply everything in here by 6. So it will be C6H12O6. All right. So this is just basic. Like I think you probably guys took this in high school. So monosaccharides, they're classified by the location of the carbonyl group. We have something called aldose and something called ketose, all right? And what's the difference between aldose and ketose? Let me guys show you. So can you see this? This is an aldehyde or an aldose, and this is a ketose or a ketone, okay? Now the difference is this carbonyl group. Do you see the carbonyl group in here? So the carbonyl group is just basically C bonded to an O, tamam? If you look in here in the aldehyde, from the name, you can see there's an H in the name. So the carbonyl group is bound to an H, all right? So we have an H in here and it's always there. So it's probably going to be either at the like end, you get me? Or like the C is going to be at the end, like it will start there, the aldehyde, and then the full like sequence is going to start, or it's going to become a ketone. What is a ketone? In a ketone, in a ketone, we do not have an H in the name. So we don't have H. So it's going to be like C, and then from it will be bounded to either another C, it's most probably another C, or anything else, all right? What I mean by there's no H, I don't mean in the like composition, there's no H. Obviously, they're going to be an H, but the carbonyl group itself, the C double bond O, is not basically bonded to an H. Tamam? This is the difference between an aldehyde and a ketone. And then another thing that helps us like classify monosaccharides is the number of carbons in the carbon skeleton. So basically, you guys know glucose and galactose. How many carbons are there? Do you guys know how many carbons are there in glucose? It's right there, guys.
6.
Slay, okay. Perfect. So 6. So this is something that we can classify like a monosaccharide with. All right. These things are just basics. We're just like slowing our way into it, easing our way into it. Tamam. Now we have basically straight chain aldoses and ketose sugars. Okay. We said إنه نحن عنا aldose and ketose. And you guys, let's look in here. Wait 1 second. Okay, let's look in here. Do you see the carbonyl group? What is the carbonyl group? As we said, the carbon double bond with the O. So if you look in here, it's always connected to an H. So we have C double bond O, H. While in here, the C double bond O, it's connected to other C's. It's not connected to an H. All right, so this is how we differentiate between aldose and ketose. Okay. طبعا يعني what's the importance of this? It's just for you guys to like know that we have a lot of different kinds of like sugars, tamam. Like there's no like significance that you guys have to do like medically, tamam. Um, in here we can look at glucose and galactose. All right, both of them have basically how many carbons? 6, right? So we have 1, 2, 3, 4, 5, and 6. So we have 6 carbons in both of them. And if you look at the structure, like overall structure, it kind of looks the same, right? Like we have here the carbonyl, sorry, here we have, yeah, the carbonyl group bonded to an H. So this is an aldose. And then we have HCOOH, OHCH, like it's kind of the same until we reach C4. صح? When you look at C4, what's the difference between the glucose and galactose? Can anyone tell me? What's the difference that you see? Like it's really like visible.
The position of H and OH is flipped.
Exactly. So if you guys look at the position of OH and the H. So on carbon 4 in glucose, the OH is on the right side, right? And then the OH in the galactose is on the left side. And if you guys look at them, if you like, they kind of mirror each other, right? Like if you flip them upon each other, they're gonna like be the same thing. So they are some kind of an isomer. Can someone tell me what an isomer is?
There are different types of isomers, but
Yeah, like
same
for
it
now,
can
just I
be
want to
like
know what is an isomer.
same like molecular formula, but they might have a different structure or different function.
Okay, perfect. So if you look at if basically someone gave you C6H12O2, sorry, O6, C6H12O6, you can think of either glucose or galactose, right? And how do you know which is which? From looking at the structure. So isomers are basically they're more molecules that have the same formula, but when you look at their structure, there's a little bit of a difference in them that basically identifies or like makes them special. All right. And why is this important? Like, why do we need glucose to be different than galactose? Do you guys have an idea? So why do I need for functional differences for enzymes? Exactly. So basically, the enzyme that breaks down glucose is not going to be the same enzyme that breaks down galactose, and their function is going to be a little bit different. All right. That's why we have these structural differences that we like. If you see the formula, you're not going to know, but the enzyme, when it like meets the structure, it's going to know like, oh yeah, this is glucose. So basically whatever is supposed to break down glucose would know that, oh, this molecule is mine. You get me? Tamam. So this is everything you need to know here. So there is a rat question, as you can guys see. How would sugars interact with water? Do you guys have any idea? So do you think sugars are going to like interact? Like, how do you think it will interact with water based on whatever you guys like took?
Hydrogen bonds.
Okay, it will form bonds. Yes. Okay, we're going to talk about this like right now. So what happens is usually when we draw the like you see in here, sorry. You see in here when we are asked, like when you were back in high school and like your chemistry teacher is like, okay, can you like write for me how like draw for me the structure of glucose? We would draw it as a linear structure, all right? Because that's the easiest thing for us. But in reality, all right, in aqueous solutions, they form rings. Okay, so this is how they react with water. Once they're with the water, they're going to form bonds, and this bonds is going to make it easier for them to form rings. Okay, and basically you can see in here like this is how the structure that we basically write, like the easier one, the linear skeleton. But once it goes into the water, we can see how some structural changes happen. Okay, which allows, so it will lose a hydrogen in here. Okay, and then you can see how like here we had double bond with the oxygen, and then the double bond is lost, and then it becomes a hydroxide. But you guys don't need to know this. You just need to know that basically like sugars, once they are or like monosaccharides or polysaccharides, once they are in water, they're not going to be a linear skeleton, they'll form rings. All right. And glucose specifically is an equilibrium between the ring and the open form at the pH of 7.4. So basically, what's the normal pH in our body? 7.4, like 7.35 to 7.45. So like about within that range. So in our bodies, the glucose like basically exists in an equilibrium between the linear, the basically, yeah, the linear or the like the, you see this is an open form. Like it's not fully closed, but it's kind of still open, and the ring form. So it's somewhere in here. All right. These are just, guys, like boring information صراحة. Okay. Now we said isomers. What are isomers? We said they are basically two molecules that have the same identical chemical formula, but when we look at their structure, it's different. Hello? So we have atomic differences that makes them look like they have different structures, and these are basically structural isomers. Okay? So yeah, that's all in here. Now let's go into the kinds of isomers. We have something called stereoisomers, right? So what are stereoisomers? Stereoisomers, they have the same chemical formula, but when you put them in a 3D orientation, it's going to look different, like glucose and galactose, right? So basically they are the same linear structure, not the same linear structure, sorry, the same formula. They have the same chemical formula, but once you like put them out into a 3D structure, or you write their form, like you write their structure, you can see the differences. So glucose and galactose, what are they? They are basically okay, we'll talk about what they are at the end. So we have different kinds of stereoisomers. We have enantiomers, we have anomers, and we have epimers. Okay, these are the ones that the doctor like looked at. Okay, so enantiomers, they're a kind of a stereoisomer that are mirror images. Like if you flip them upon each other, they're going to basically show, like they're going to like collide and become one structure. Okay, so this is what an enantiomer means. It's like you're looking at yourself at the mirror. Okay, and I'm not sure if Dr. Abdul Jabbar mentioned that, but you know the difference between the D form and the L form?
Heard about it, but we forgot. I forgot.
Okay, so the difference is you can, okay, perfect. What is the difference? Someone said yes.
Was it something with dextro or levo or something with the rotation?
Basically, it's nothing like very like complicated, but the difference between a D and an L, okay? The D can be digested by our stomach, okay? We can digest them as humans, but the L, they're usually undigestible, all right? So in our body, the enantiomer that can be digested is usually the D, whatever comes after. Tamam? Okay. Moving on. L on left and D on right. Honestly, I'm not sure. Listen, like you guys did not have a transcript or like a recording. I'm basing it on whatever was given to the years before. And the years before, they looked at D as, and no, it's digestible. So D for digestible, and L is usually not digestible by our body. That's all you need to know. And you just need to know what an enantiomer means. Like it folds upon itself. It's a mirror image. Okay? This might be extra. I'm not sure if Dr. Abdul Jabbar mentioned that صراحة. Anyways, moving on. We have the epimers. Now, epimers are basically differences that happen around one carbon atom. Okay, so look at it here. Okay, so okay, the boxes are on the wrong one. Anyways, if you look at this structure in here, we have like basically carbon, 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 right? So what is the difference? The difference is at this one. It's at the second one, okay? So the difference is in here, the OH is on the left, while in here it's on the right. Tamam? I'm sorry guys for the boxes, they're on the wrong side. They have to be like, the red boxes should show the first one. Okay, so this is the difference here. So apimers, usually the difference is only at one of the carbon atoms. Okay, is this clear? Yes. Okay, and then last but not least, we have something called anomers. Now, anomers, okay, anomers, they're usually just in ring form. Whenever you see something that is an isomer in a ring form, just know that it's an anomer. Okay, that's it. So enantiomers, they can mirror each other. And then when they don't mirror each other, they're called this long name that you guys don't no need to know. So this long name can either be an apimer or an anomer, okay? Apimers, the difference is on one carbon atom, but we can't fold it upon itself. And if you look at this, I can't fold it. Like if I fold it upon itself, it's not gonna be like one perfect image. Tamam? So this is an apimer. The difference is on one carbon atom. And if you see a ring structure and they're like, oh yeah, these are isomers, and then they show you the ring structure, just know it's an anomer. Tamam? Slay? Slay. Let's move on. Okay, reducing sugar. Okay. Okay, so I'm pretty sure you guys know someone. Which type of isomer is glucose and galactose? Oh, صح. طيب. Someone tell me, what type of isomer is glucose and galactose? I'm sorry, I thank you, Hannah, for reminding me, صراحة. Let's go back. They're apimers. What's the difference between enantiomer and apimer? Okay, نرجع glucose and galactose. Okay. Someone said apimers, someone said enantiomers. Okay, maybe it was my mistake because I said they fold upon itself. But now when I look at it, they don't fold upon themselves. If you look at it, in here, at this point, they do fold upon themselves. But look at here. If I put this above this, it's not going to be in OH, but they don't, right? So what do you guys think this is? An apimer or an enantiomer? It doesn't mirror itself. Like شوفوا, I know I made the mistake at the beginning and I said it mirror itself. I was just so excited. It wasn't أصلا ما انتبهت غير على this one. But it doesn't mirror itself. Look, it only mirrors itself at this one. But look at here. If I flip this on this, it's gonna be H to an OH. OH to an H. So it's not a perfect this. But the only difference, if we look at here, if you look at all of the C's, the only difference is at C4. So this is an apimer. Whoever said apimer, صح. Did this confuse you guys?
Wait, so the enantiomer, they all match if we put them
Yeah,
on
they all
the-
match, not only the one that's different.
Okay, thank
You
you.
get me? Enantiomer, you can fully put the structure on each other. You get me? Like, let's go to enantiomer, 1 second. So look at this enantiomer here. If I flip this to this, the OH is gonna meet the OH, the C is gonna meet the C, the H is gonna meet the C, the H, the C is gonna meet the C, H is gonna meet the H, O is gonna meet the H. You get me? Is it clear? Now, someone asked, what's the difference between enantiomer and apimer? It's basically the mirroring. Like in an apimer, we can't, like, the things cannot mirror each other. Like this glucose and this mannose, they can't mirror each other. Yani if you put them upon each other, they're not going to become one structure. Hello? So if you look at what is the difference between them, you can see that the difference is only at one C, which is in here. Like مثلا you see in here, it's at C3. And مثلا glucose and galactose, it was at C4. You get me? Is it clear? Why are they not They are. But my apimer is a kind of diastereoisomers. You get me? But I don't care about the diastereoisomers, like the name. I care about the specific one, which is the apimer. So is it clear? Can I move on? I feel like I kind of confused you guys. I'm sorry. I feel bad. It's clear? Yalla, everyone, we have 17 people here. Everyone say it's clear. Actually, 19.
Wait, sorry. I know they're saying it's clear, but can you go back a little bit?
Yeah, sure. When?
للانانتيمرز again.
Enantiomers. Hon.
Yeah.
Okay.
So you said that so each and every one of the like branches will fold on top of the other,
Yeah.
sort of, but it doesn't.
I
not
think you
all-
were talking about the carbonyl, صح?
Yeah. So we don't count that. The
No,
carbonyl.
أهم شيء السيدز, you get me? Because the carbonyl is like a one structure. So المهم إنه the structure goes to the other. You get me?
Oh, okay. That makes sense. Thank you.
Yeah. So basically أنا when I say mirroring, I'm talking about the ones in the middle, okay? Like هدول اللي انتبهوا عليهم. أكيد if you put like CHO, like if you do it like this, it's not gonna 100% mirror, but it's the same structure, so it's gonna mirror. You get me?
Yes,
Okay.
thank you.
Someone said we took the L and D forms with, okay, she tells us that amino acids in our body exist in the L form, or is it wrong? طب listen, I'll double check at the end and I'll tell you. أنا بتذكر I watched Dr. sorry, not Abdul Jabbar, Dr. So basically, doctor that gave it last year, Al Jadad, said that D is digestible. So that's why. But wait, let me. Yeah, you can see here. So basically, a monosaccharide, what is the difference between D and L? It's important because your body can only metabolize the D form with some exceptions, all right? So some exceptions are okay, but listen, like Jana, the thing you're talking about is an amino acids. Amino acids are different than glucose. Like we're talking here about carbs. For carbohydrates, D is the form that we can metabolize in our body, that we can digest. L is not the form that we can digest. Whatever the other doctors told you for like amino acids is different. All right? Is this clear? I just had to double check. I got scared. I think I'm not sure. Like for the proteins, صراحة, you have to double check with your lecturer because I have zero idea about the D and the L and the proteins. But for the sugars, it's the D that's digestible by our body. Okay. So I'll move on. Is it clear, guys? Okay, perfect. Now, reducing sugar and HbA1c formation. Okay, I'm pretty sure you guys know someone that has diabetes. Like I'm pretty sure, like even if you don't, if it's someone not in the family, but you know someone that has diabetes, or like you've heard of someone that has diabetes. Okay, now when a patient has diabetes, the things that usually like the warning signs, or like the things that people like alert them, like alert the doctors and oh someone might have diabetes, are basically the three symptoms, which is polyuria, polydipsia, and like polyuria means you go to the bathroom a lot, okay, and polydipsia you drink a lot of water, and what's the third? I forgot. But you know, the idea is you go to the bathroom a lot, and when you go to the bathroom a lot, the volume of the urine is high. Okay? Why? Because usually we have reducing sugars inside the urine. Tamam? It's kind of embarrassing that I forgot the last one, but yalla guys, we move on. It's three. مو مهم. المهم, so what is a reducing sugar? Okay, reducing sugar, they're basically all kinds, like almost all monosaccharides and most of disaccharides, except for sucrose, are reducing sugars. And when we say reducing sugars, it means they reduce a specific reagent. And what is this reagent? It's the Benedict reagent. Tamam? So basically, let's say I have a patient who has diabetes. I took their urine and I was doing some tests. One of these tests is I added Benedict reagent to the urine, and then I will look for a changing color. طيب, this changing color, can someone like tell me why do we have this changing color? Like, do you guys, if you don't understand it, I can explain it. But do you guys have an idea at least, you know, why do we have this changing color? Okay. I love the silence. Anyways, guys, I'll explain it. It's okay. For the change in color, tamam. Remember how polyphagia is the third one? It is. I think it was, but صراحة, like it was in my head, but I was like, really? But you're right, polyphagia, yeah. Anyways, let's move on from that. بس ركز هلا reducing sugars. So for reducing sugars, okay? Reducing sugars. So from the name, they reduce. تمام? They reduce this reagent. So what will happen? The aldehyde group that is usually there, okay? It is oxidized to a carboxyl, forming gluconic acid. This is a bunch of like weird names, okay? But يعني simply, okay? The basically we have a structure, okay? Reducing means it gives up the hydrogen. So it will give up the hydrogen, the aldehyde group will give up the hydrogen, it will become a carboxyl. And this carboxyl, because if you guys remember, carbonyl, the initial carbonyl, what was it? It was C double bond O, right? Aldehyde, what was it? It was C double bond O, an H here and an R, صح? So when an aldehyde, we want to change it to a carbonyl, we're letting an H go. So this is the reduction. The reduction is basically this H is going, and basically it's going to form this gluconic acid. تمام? This gluconic acid is going to cause the change in color. طبعا, as you can see in here, we have different colors. So if it stays the same color, it means we don't have any sugar because nothing is reducing the agent. تمام? But if we have مثلا green, this means we have a low concentration. If we have yellow, this means like, okay, it's a bit higher. Orange, a bit higher. Red, like, okay, it's way higher. تمام? Do you really need to know the percentages? I'm not sure, because صراحة for me, if I was the person who's studying this, I'm not going to study the percentages. Just know that green is the lowest, red is the highest, and then in between we have yellow and orange. Okay? Do you guys understand the idea? It's just like يعني you're trying to test it. Okay? Okay, that's a very important question. Since reaction involve aldehyde groups, this test also work on ketoses. I'm not sure, صراحة. But like, since it only like theoretically, since we're saying the aldehyde group is the one that's oxidized, so theoretically the answer to your question is no. But I'm not 100% sure to tell you like no for sure. But based on whatever the reagent is, yeah, it is a no. Do you get me? But I can double check for you. Like I'll double check for you at the end, don't worry. Moving on. Is this clear, guys? Yes. Okay. طيب هلا HbA1c. When we have a lot of sugar in our blood, in our body, what happens is the glucose is going to seek the blood. So the hemoglobin, okay, the hemoglobin and the glucose are going to react, and then we're going to have something called HbA1c, which is the glycated hemoglobin. So hemoglobin is going to have a glucose on it, and this is a very, very important phenomena. Why? Because it helps us, specifically in diabetic patients, we can know if they are like taking their medications or if they're not. Because HbA1c, it indicates the long-term control of blood glucose. Okay, so basically you can have a patient that comes to your clinic and is like, yeah, doctor, I'm taking my medications, I'm doing everything, and then they act like they're compliant, but then you check their HbA1c and it's like 7 or 8. This will show, basically they're not telling you the truth. They're basically their blood glucose control is really, really bad. So they're probably not compliant to their drugs. Okay? So HbA1c is just there because when we have a lot of sugar, the reducing sugar in our blood, it will react with the hemoglobin, and we're gonna have HbA1c. تمام? Now, these HbA1c, they can end up forming advanced glycation end products. And these advanced glycation end products usually happen in the advanced stages of the disease. So if we see the advanced glycation end products, we know the diabetes is being poorly controlled. It's the patient is not compliant to their medications, and we have to do something about it, because you guys will later on take, diabetes has a lot of complications, and we want to protect the patients from these complications. تمام? Now the very, very optimal, like the huge, like the normal blood glucose HbA1c is at 4 to 6. Tamam? So we aim in diabetics to give them like drugs that would help them to keep their HbA1c, or to keep their blood sugar control within this range. Tamam? This is all you need to know, guys. It's really nothing. It's just glucose plus hemoglobin, HbA1c. HbA1c is important for diabetes, helps the long-term control of the blood glucose and so on. تمام? The idea of, I wanted to just explain, the idea of having sugar in your urine and having sugar in blood. In diabetes, we have a dysfunction in the basically capacity of absorbing the sugar. So when you eat something, usually your body your liver is going to take all of these glucose and will form glycogen. And I'm pretty sure you guys are going to take glycolysis and like all of these processes. But just for now, just know that basically our body will take this glucose. The liver is going to take all of the glucose in our blood and store it. Okay? But in diabetes, there is a dysfunction, and this dysfunction is going to cause the glucose to stay in the blood. And because the glucose stays in the blood, you know how our kidneys filter the blood. So a lot of sugar is going to go into the urine, and that's how we have the glycosylated hemoglobin and the glucose in our urine. Tamam? Is it clear? Okay. How are we feeling up till now? I hope you guys are not confused. Is everything okay? Okay. So let's move on then. Now we're going to talk about oligosaccharides. From the name oligo, it means that basically, so again, we have monosaccharides, just one. Disaccharide is 2. Oligosaccharides means 2 to 10. Okay? So from 2 to 10, if we have 2 to 10 monosaccharides, we're going to have oligosaccharides. Usually oligosaccharides, we can take them from the diet, like whatever you eat, you might have. Now, oligosaccharides are healthy. And when I say healthy, why do you guys think it's healthy? So do you think if it's better if you take like monosaccharides or oligosaccharides? Just generally, before knowing why. Natural sugars present in foods. Okay. These are oligosaccharides, I think, okay. Oligo. Actually, oligo is healthier for our body. Why? Because oligosaccharides, they increase the viscosity of gut contents. So when they increase, okay, how do they do that? So basically, oligosaccharides, they're usually metabolized by the bacteria that's found in our colon. So we have bacteria in our gut. Tamam? These bacteria, once they break down the oligosaccharides is going to, so we know whenever we eat anything, it's in the colon and it's getting broken down, right? So we have, what is it called? We have, we won't only have مثلا sugars, we will have a bunch of things, okay? So when the gut bacteria try to break down and metabolize oligosaccharides, these metabolized oligosaccharides, they're going to increase the viscosity of all of the contents in the gut. So when you increase the viscosity, and by viscosity, do you guys know what viscosity is? Viscosity is you know how it kind of is the texture, it's not going to be watery, no, it's going to be thick. So it will increase its viscosity. Tamam? This increase in viscosity, what will it do? It will decrease the postprandial plasma glucose spikes. And when I say decreases postprandial plasma glucose spikes, it sounds all fancy, but the idea is, it will just prevent the glucose spike after we eat. So usually if you go and you eat, let's say, if someone goes and eats a piece of chocolate, would it be the same as the glucose spike, would it be the same as someone who just went and ate fruit, or like someone who ate like something that's healthier? Akid no, right? So basically, oligosaccharides, they will increase the viscosity of all of the contents. So the glucose spike that happens after the food is gonna not be as high. You get me? So it will slow it down. And this slowing down is basically healthier for us. Okay. And another thing it does is it increases the time amino acids and sugars are present in the lumen. So it will delay the feeling of hunger because you feel satiated. So basically, you have food in your gut. So you feel like, I don't want to eat more food. Do you get me? So basically, what it does is it increases the viscosity, it prevents the spike, and it increases the time as for the time where amino acids and sugars are in the gut or in the small intestine, so we won't feel as hungry, and that's why it's healthier. So basically, when you have a patient that has diabetes or a patient who has obesity or like anyone who's just trying to live a healthier lifestyle, you tell them increase your fibers, increase, like if you want to have something sweet, have something sweet that's like a fruit, because fruits have, like apples for example, they have a lot of fibers, and those fibers will help basically with the whole, like, will help your gut, and it will make you live like a healthier lifestyle. Okay. What else? Formation of glycosidic bond between two monomers in an oligosaccharide is a condensation reaction involving the elimination of a molecule of water. So oligosaccharides, okay? We have let's say we have an oligosaccharide and an oligosaccharide, and we want to fuse them together, okay? Actually, no, I'm sorry. Like, let's say we have two different sugars and we want to like put them all together to form an oligosaccharide. We have a monosaccharide, like 8 monosaccharides, and we want to form an oligosaccharide. How do they bond together? The bond that happens is a condensation reaction. And when we say condensation, think of it. When we say condensation, we're condensing something. So the water is gonna, like, imagine if you have like, let's say 2 molecules and we have water in between them. If you condense them together, the water is gonna go out. So the monomers in the oligosaccharides are combined together by a condensation reaction, which involves water leaving. So we will have an elimination of a molecule of water. All right? Is this clear? Okay. Do we move on? Or does anyone have any questions? Can you repeat the passport? Okay. Okay. It doesn't involve amino acids. Listen. So when at the beginning we said oligosaccharides, they are made up of a bunch of monosaccharides, right? From 2 to 10 monosaccharides. So those monosaccharides, when they come together to form an oligosaccharide, what will happen? A condensation reaction will happen. And when I say a condensation reaction, just imagine, okay, if I have two, let's say these are monosaccharides, all right? And then in between the monosaccharides, they're not together yet, okay? In between them, imagine that we have water, okay? So if you press on these things, isn't the water gonna like fall? Like you get me? So when you condense two things together, there will be no space for the water, and the water is like, it's like a viscous material, like it's all together. So it's not gonna compress, it will just slide away, right? So in a condensation reaction, think of it this way. Whenever I have a condensation reaction, we'll have, once they're condensed, the water is gonna go out. So usually the formation of the glycosidic bond, so when we have a glycosidic bond between two monomers, what happens is it's a condensation reaction and the water is gonna be eliminated. So for each bond between, I don't get why eating fog. Okay, wait. So for each bond between the two, a water molecule is eliminated. Is this clear? And I'll explain why fibers decreases the probability. Okay, so fibers decrease the probability of developing obesity and diabetes because now the main issue with diabetes, before obesity, the main issue with diabetes is that we have Okay, I'm sorry. طيب, okay, I'll explain this part now. Okay, so the main issue with diabetes is إن إحنا we have a lot of sugar in our body, and for type 2 diabetes, usually it is something that happens due to your poor choices in food. Okay, if someone like type 1 diabetes is genetic, so people get it just like genetically. تمام. Type 2, mainly it's because of your lifestyle, the things you eat, and so on. So usually before type 2 diabetes happen, the patient is going to have insulin insensitivity. So they're going to have insulin resistance. Their body is no longer responding to insulin. Why? Because they're eating a lot of sugars, and they're not eating the good types of sugars. They're eating the bad type of sugar. Now, what is the difference between the bad type and the good type? The bad type of sugar is going to raise your glucose spikes. And whenever you have an increase in glucose spike, your body is going to go under stress. تمام؟ when you eat, let's say, a bar of like chocolate, ما ضروري واحد. If you eat like a bunch of like a lot of bars of chocolate, and your glucose will spike up to a very high level, and your body is going to go into it will go into like a phase of stress where it's going to try to lower the glucose back into the normal, the threshold, all right, the normal threshold in our body. So oligosaccharides, which are fibers, when you eat them, we won't have this crazy spike. So the body is not going to go under this crazy stress where like, oh my God, I need to like lower it down into the threshold. Okay, so this is healthier for us, because insulin resistance, which causes eventually, like if you don't like treat it for a long period of time, it will cause diabetes. Insulin resistance happens because when you eat a lot of sugars and your body is under a constant stress of high a lot of glucose spikes, your body is just going to become insensitive. And okay, my glucose spike is really high, but okay, that's the normal, so no need to do anything. You get me? But when you eat something that has a lot of fibers, what happens, the glucose spike is not going to happen, it will be decreased. So your body is not going to have to go through the stress, and it won't develop insulin resistance. All right? So this is for the why fibers are healthier. And another thing the fibers do, which is about the amino acids, we said it increases the time of amino acids and sugars present in the lumen. Okay, so what happens is when you eat fibers, the body is not able to digest the fibers. Okay, this is the thing with fibers. Your body will not fully digest the fibers. But because the body is not fully, so basically the body will start working on the fibers and it's not digesting it. So the fibers are still there. So it were kind of like the body will be think of it like that. No, we have something going on now where the body is trying to break down the fibers, but the fibers are not being broken down. So it's kind of delaying the process of other things being broken down. So it will increase the time of amino acids and sugars in the lumen of the intestine, so you're not going to feel hungry so you're not going to feel hungry so fast. Do you get me? Is it clear? Okay, wait guys, I need to. Is it clear for everyone? Everything? Okay, wait, guys, I just need to like increase. Just 1 second. I'll just increase my AC because I'm really hot. Do you guys have any questions? Okay. Do you guys have any questions? No. Okay, slay. Now to this. Okay, this slide looks so scary, and I know, but the only thing that you really need to know, guys, in here is that oligosaccharides, okay, they can be helpful, okay, as cell markers. And when I say they're helpful as cell markers, we have a bunch of examples in here that shows you how they can be really helpful in the body. Okay, do you have to know these? I don't think so, honestly. I really don't think you have to know these because they're kind of a lot, but let's go through them just for general knowledge. Okay, so A, what does it say? You have to know كمان إنه oligosaccharides usually they are bound to proteins to form glycoproteins, or they're bound to lipids to form glycolipids, and these help in formation of cell markers. Like, okay, so for A, it says glycoproteins or glycolipids on the plasma membrane interact with lectins in the extracellular matrix. This sounds like a bunch of, I don't know, like a word salad, okay? Just look at here. We have a plasma membrane protein, okay? And then with this protein, we have an oligosaccharide chain. And it's out. Why? Because it's waiting for something to bind to it. That's it. So oligosaccharides, they can be good for cell markers, all right? Okay, B, in here, look at this. This is a virus, and this is the cell, right? We have a plasma membrane protein. This plasma membrane protein is basically exposing its oligosaccharide, right? So this oligosaccharide, it will bind to the viruses, and it's a way for the virus to get in. Okay? That's it. You don't really have to know these guys. Like, just know that it has a function as cell markers. That's it. Look at C. C, we have bacteria, toxin, like cholera, binds to a surface glycolipid before entering a cell. So basically, it's kind of like it's a way into. So the virus will bind to the oligosaccharide and go in. The toxin will bind to it and go in. The bacteria here will bind to it and go in. You get me? So these are like ways where microorganisms, and so like, okay, the doctor is trying to tell you that we have a cell. The cell can expose its oligosaccharide. It's there. It's a cell marker. It's something that is usually on the cell wall or cell membrane, depending on the cell. Anyways, that's on the usually part of the cell surface. Okay, so it can be something that allows either viruses, toxins, bacteria to go in, or it can be really helpful because it can help basically, it will bind to something called p-selectins. You're going to take this later on, like in second year. It's not important now. It's just like a protein, okay, or whatever that goes out of the cell. It will bind to it and it will cause interactions between two cells. So it can facilitate two cells communicating together. Do you get me? Right. Where's the chat? Okay. Is it clear? So now we have F. It's saying that basically the mannose 6-phosphate, it has an oligosaccharide, and this oligosaccharide is the thing that will bind to the enzyme. All you have to know is oligosaccharides exist on the surface of on the surfaces of the cell. They can be bound to a plasma. They can be directly bound. They can be literally like bound to a plasma membrane protein. They can be bound to a glycolipid. Like you see here, it's a glycolipid. They can be bound to a protein that exists there or a receptor, and they will help in cell signaling, or they can help in allowing microorganisms to infect the cell. Tamam? This is all you need to know. Do you really have to know the specific details? No. Okay? Now, we talked about mono, we talked about di, we talked about poly, we talked about oligo. Now, if we said oligo is 2 to 10 monosaccharides together forming the oligo. But if we have more than 10, what do we call it? Can you please repeat the last point from the previous slide? Is it the F or what I said last? Okay, F. So F, it's just saying that basically, one second. Okay, so it's saying that the mannose 6-phosphate, all right, which is basically something we're going to talk about later, by the way, at the end of the lecture. The mannose 6-phosphate in here, okay, it's a receptor. And this receptor is usually found where? It's found on the Golgi, the Golgi complex. So this mannose 6-phosphate receptor, it's going to have an oligosaccharide going out of it, okay? And it can bind to the lysosomal enzymes. You get me? Like, okay, look at this enzyme. This enzyme has an oligosaccharide. Look, okay, wait, just to make it clear. You see this enzyme here? You see the oligosaccharide? Okay, then we have the mannose 6-phosphate receptor. Okay, so the enzyme with the basically oligosaccharide, what will happen? It will bind to the mannose 6-phosphate, and then it can basically say like, oh, now I'm ready to take me to wherever. Okay, yani it will just activate the function. Is it clear? You don't really need to know this. Yani the very, very details of it is not important. You just need to know and know it's something that is found on the cell. So oligosaccharides can be bound to a glycolipid or a glycoprotein, glycolipid or a plasma membrane protein or glycoprotein, and on the surface of the cell membrane, and they are involved in basically cell-to-cell interaction, whether it's with a virus, bacteria, a toxin, other cells, anything. Okay, تمام. Okay, we're transporting the lysosomal with the help of this or the entire vesicle. Basically it's just like the lipopolysaccharide is just a signal. Yani when the oligosaccharide on the enzyme. So this is the enzyme, and it has, let's say, this out of it. Okay. Oops. This out of it is the oligosaccharide. All right. So enzyme, oligosaccharide. So, and this is the mannose 6-phosphate. If they bind together, this will tell the cell like, oh yeah, I need to remove this enzyme and like let it go into a vesicle, into the lysosome. Do you get me? But you don't really need to know this. That's why I didn't go into the details of the details. Like, it's just, I told you again, for the 100th time, it's just know that oligosaccharides, they're involved in cell signaling and cell, it's just on the surface, it's a cell marker, it's on the surface of the cell. It can help bacteria, virus, toxins go in. It can help the cell basically communicate with another cell, help basically enzymes inside the Golgi, like to basically to transfer them into, like they'll be tagged so they can go into they can be transferred into the lysosome. Is this clear? Okay, everyone? Okay, perfect. Let's go. Okay, now polysaccharides. We said oligosaccharides 2 to 10. So if we go after 10, what will happen? We'll have polysaccharide. So from the name, poly means we have a lot of monosaccharides together. Okay? And then polysaccharides, what's important about it is that polysaccharides are the most important form for storage. They're the main they're the main storage. I said remember when I said our liver basically will absorb all of the glucose and will try to make it into a form where we can store it. So yeah, we store polysaccharides, which is basically the glycogen. Tamam? So the main storage form of polysaccharides are either plant starches or animal derived. Now, plant starches are something that are in the plant. So we have amylose and amylopectin. And the difference between amylose and amylopectin is just that amylose is a linear glucose molecule, okay? And it forms just alpha 1 to 4 bonds because it's linear. So this is the bonds that it forms, 1 to 4 bonds, linear, okay? Amylopectin, on the other side, it is a branched glucose molecule. So we'll have the normal alpha 1 to 4 bonds, and then we're going to have an extra bond, which is 1 to 6. Okay? So amylose is just straight, linear. Amylopectin, branched. So amylose is going to have the 1 to 4. The amylopectin is going to have 1 to 4 and the 1 to 6. Guys, do you know what 1 to 4 means or 1 to 6 means? Carbon. Okay, yeah. Bonds. Yeah. So basically, the position where the glycosidic bond form. Exactly. So the glycosidic bond usually will happen between C1 and C4. Okay? This is the alpha 1, 4. This is in the linear structure. But when we're talking about the branches, it's going to be 1 with 6. 1 with 6. Okay? Slay? Clear? Okay, so now the animal derived, and from the name animal derived, made by animals, where kind of animals? So as glycogen. Glycogen is branched. It has 1 to 4 and 1 to 6. Now, glycogen usually is stored in the liver. It is a central energy storage organ in animals. You know, basically, we talked about, like when we were talking about diabetes, we said, the liver, it's going to absorb all of the glucose in the body. And after it absorbs all the glucose in the body, what happens? It will start glycolysis, which is basically formation of glycogen. And I'm pretty sure you guys, did you take the lecture or no? You did. Okay, slick. So you know what I'm talking about. So glucose absorbed by the liver, a bunch of reactions happen, and we're gonna have glycogen. Glycogen is usually stored in the liver because it's the most important like organ for storing the glucose. But glycogen, come on, is available a lot in the muscles. And why do you guys think it's available a lot in the muscles? Specifically skeletal muscles, not any kind of muscles, skeletal muscles. Even other muscles, but يعني it's mostly abundant in skeletal muscles. Energy storage. Exactly. So basically, نحن when we're trying to like, what is it called? When we want to like run, we want to do exercise, we want to do anything, we need energy. So what are we using? When you run, what are you using? You're using your muscles. So basically for very fast energy supply, where the glycogen is going to be broken down into glucose, okay? So that's why we have glycogen mainly stored in the liver, and then we have a little bit of glycogen that is usually found in the muscles, specifically the skeletal muscles. I think all muscles have glycogen stores, but it's mostly abundant in skeletal muscles. Okay? Clear? Okay, here they're saying monomers of amylose are released slowly by amylase. So you guys know that we have, specifically in our mouth, by the way, we have the enzyme that's called amylase. So when you eat, like, let's say bread, the enzyme in our mouth that's called amylase will start breaking down the amylose in the bread or in whatever carbohydrate you ate. Tamam? Now, the monomers of amylase are going to be slowly released. And that's good. Why? Because since they're slowly released, we don't have the spike, the really high spike. And again, we're talking, I know this is better and it reduces your risk for obesity and type 2 diabetes. طبعا amylose is not found in any kind of like, okay, I said bread. I don't think bread has amylose. Maybe like the brown wheat, the wheat bread, that probably has amylose. But normal bread, white bread does not have. It's refined sugar, like 100% it does not have. But like things like lentils, legumes, long grain rice, all of these are high in amylose. And that's why, when people start dieting and like, hey, they tell them like, oh, like it's better for you to have the wheat bread or the brown bread. It's because of the amylose. Tamam? Again, because we're trying to decrease the spike after every meal. Is it clear? Okay. Now, we said إنه عندنا amylose and amylopectin. Amylopectin is branched. صح? Amylose is not. It's linear. Now, amylopectin, because it's branched, think of it. Like if I have, okay, so we have, well, everything I have in here is makeup. That's funny. Anyways, if I have something that is branched like this, all right? Like when I want to I'm an enzyme and I want to break it down. So isn't it easier for me to just like break this bond? And then I have a glucose molecule that is just free, right? So amylopectin, when you break it down, what happens is it's going to cause a release, like a rapid release of glucose into the blood. So we're going to have this sugar spike. تمام. So higher intake of amylopectin rich foods is gonna basically cause like it's not gonna cause, but it will increase the risk of having obesity and type 2 diabetes. That's why, like I was just saying, bread is not gonna have like the white bread, obviously it's not gonna have amylose, it's not gonna have a lot of fibers, it will have amylopectin. So bread, potatoes, corn, short grain rice, all of these have amylopectin, and because of the branching, it's easier. We're gonna have the rapid blood sugar spike. Another thing, guys, you like remember how we said the rapid sugar spike, and because it's not fibrous, so basically we're gonna feel hungry really fast because خلاص you like your body like was under stress, it worked so hard to like put down the glucose levels, it's gonna get tired and it's gonna be hungry again. And remember the amino acid and the glucose that stays in the gut, it's not gonna happen. So what will happen? We're just gonna feel hungry faster. تمام. Now I know we're saying, okay, amylopectin is branched, and it's like, and we're saying that it causes glucose spikes, and it kind of is, I'm not saying it's like unhealthy and it's the worst thing ever, but yani there are other healthier options. But we said in here that glycogen has branches too. So is the glycogen the thing that we do unhealthy, Kamal? Now, the difference between glycogen and amylopectin, no, I don't know if it's unhealthy. Obviously, it's not like anything will have more branches than the amylopectin. And if you guys think of it, it makes sense because now we're using glycogen as a storage material. And if I want to release the glycogen, if I am in let's say I'm in starvation mode, I haven't ate in like 3 days, okay? So my body needs sugar, and I don't have any sugar, like I don't have anything to take sugar from. I only have my glycogen. So it will make sense for the glycogen to be branched. And you can see in here, it says the branches are more frequent and they're shorter. So it means it's easier to break down. You get me? So basically, if you think of it, in glycogen, this is an advantage, but in like the food that we eat, it's a disadvantage. Because the glycogen is something that's regulated by our body. On the other hand, anything that you're eating is not regulated. Do you get me? Is it clear? Hello? Okay, you guys can hear me, right? Do you have any questions up till now? No questions? Is it clear? Can I move on? I think the checkpoint is after this. Yeah. So how are we feeling? Are you guys okay? This cat is asking. Are you guys okay? It's easy up till now, right? Okay, the checkpoint is gonna reach like Mars. But guys, is it okay? خلاص, shall I move on? Is it easy? Do you guys have any questions? Is there anything that's kind of like weird? Or عادي خلاص, I can move on. Because we're going to go to the second part, which is احنا لا خلصنا carbohydrates. Now we're going to talk about what? Glycosaminoglycans. I don't even know how to say this word. It's just gags, okay? Just say gags. شو guys, امشي? Shall I move on? Yes, move on. Stay. Okay, now we're gonna talk about glycosaminoglycans. From the name, glycosaminoglycans means it's protein plus glucose. So when we have protein plus glucose, we have a killer combo. Okay? Where are they found? Usually, they usually make up the extracellular matrix. Okay? So GAGs are usually found on cell surfaces, the extracellular matrix, and in secretory vesicles. Hello? They're highly negatively charged. What is the difference between amylase and amylose? Amylase is the enzyme that breaks down amylose. Is it clear? Guys, anything with an A's, like DNAs, breaks down DNA. What else has an A's? Glucokinase. You guys took it. In glycolysis. Yeah. So basically it's an enzyme. Well, amylose is the structure. So amylase works on amylose and it breaks it down. Cool. ATPase, yeah. Anything with an A's usually. حتى, like if you think of it, hydroxylase, kinase, phosphorylase, anything with an A's is an enzyme. So like it's not a structure, but rather an enzyme that will break down whatever structure that we're saying. Okay, good. Now, back to extracellular matrix. So GAGs, they're highly negatively charged, okay? Because they're negatively charged, this makes them viscous. And when we say viscous, what do we mean? Does anyone know what does the word viscous mean? It's the silence for me. High viscosity. Okay, yeah, it is high viscosity, but what does high viscosity mean? So when a structure is viscous, what do we mean? Thick. Exactly, they're thick. So it doesn't flow easily. Slay. So when we're saying GAGs are highly negative, and because they're highly negatively charged, they're viscous. Let's think of chemistry or whatever it is, physics maybe, I don't know. Two molecules are negative. What will happen? Are they going to attract or are they going to repel? They're going to repel, right? So, oh my God, I don't have it here, but you know the magnets we used to play with. Do you remember them? They look like the two magnets. Yeah, these. So basically when you're trying to put negative, like you're trying to put the opposites together, they're going to be like, you're going to feel like a charge in between that's preventing them from going together. So because GAGs, they're highly negatively charged, this will cause them to be viscous. They're never gonna they're not compressible, okay? So I cannot just compress them. They're always gonna be this invisible, like invisible charge in here that's preventing them from getting together, okay? So this is a very important thing because okay, we're gonna take a bunch of GAGs in a bit. Where are they usually found? Like any kind, like heparan sulfate or like chondroitin sulfate or like hyaluronate acid or hyaluronic acid. Where are these GAGs usually found? Give me one thing that is really like where it's really important for this incompressible thing to happen. Hello guys, give me a structure. Joints. Perfect. That's what I'm looking for. Joints, exactly. So when you're walking, or even your joints in here, you don't want your joint to like, I don't know, collapse or like you want it to be like easy flowing. Like when you're walking, all right, your knee is like going there, out, in, out, in, out. If there was no synovial fluid, which is made up of GAGs, do you think this in, out, in, out, in, out would have been easy? No, because the bone is going to be on the bone and it's just going to like wear and tear each other and it's just going to be creaky, it's going to be painful. So this is where the viscosity plays. They're negatively charged, they're viscous, so they're not gonna basically, it's gonna be less compressible. They're not gonna be fully compressed. They're just gonna basically lubricate and make the movement of the joints easier. All right? Slay. So, the most important thing to know is negative, viscous. Okay? And they're viscous because they're negative. Now, they're heteropolysaccharides made up of long unbranched polysaccharides with repeating disaccharides. So they're heteropolysaccharides. Heteropolysaccharides. So we have a lot of polysaccharides. And these polysaccharides have disaccharide units, all right? And these disaccharide units are the important ones because these disaccharide units are the things that we're going to keep on talking about. So you see the disaccharide units comprise of two modified sugars, N-acetyl galactosamine or N-acetyl glucosamine. And glucuronate or iduronate. And now we're going to talk about these more. But think of it again. We have polysaccharide, and then we have unbranched. This is, yeah, you see, this is unbranched polysaccharide. And this polysaccharide is made up with repetitions of disaccharides. And what are these disaccharides? Acetyl glucosamine, acetyl galactose together. So you start. Okay, I'm sorry. So the last thing we said, no, let's break down the name together, right? So N-acetyl galactosamine. So if you look at the name, it's literally acetyl. So N-acetyl is unchanged. Then you either have galactose or glucose with an amine. And we're talking about glycosaminoglycans. So we have an amino acid with a glucose. So it's either going to be N-acetyl. So N-acetyl is there. It's either going to be galactose or glucose and an amine. This is the only N-acetyl and amine are there. The only difference is in the middle. Okay? Okay. And then we have the glucuronate or iduronate. صراحة, I don't know how to help you memorize that, but it's just either glucuronate, which is glucose, and just ronate. I don't know what ronate is, or iduronate. Okay? Now, again, as we were talking, the generalized structure, we have an unbranched heteropolysaccharide chain of repeating disaccharides. These repeating disaccharides, they can either be acidic or amino sugars. So acidic sugars are basically glucuronic acid and iduronic acid. And from the name acid, glucuronic acid, or it's the glucuronate, iduronic acid or iduronate. Okay? This acidic sugar can come with an amino sugar, which is basically the one we're talking about, N-acetyl glycosamine or N-acetyl glucosamine. Okay? And then they will come together, forming the glycosaminoglycans. All right? Is this clear? Wait. Yes. Okay. So this is clear, I hope. Now, we said that the structure is highly negative. Why is the structure highly negative? Why are glycosaminoglycans very negative? So basically, the carboxyl groups inside the polysaccharide, okay, because, okay, I'm asking why is it highly negative? Because if you think of it, it's polysaccharide. And like, we didn't say when we talked about carbohydrates, we did not say that what is it called? We did not say that that polysaccharides are negatively charged, right? Because they're neutrally charged. But in glycosaminoglycans, what happens is that the carboxyl groups, they'll be deprotonated. Okay? So a proton from the carboxyl group is going to be removed. So when we say proton, we mean a positive charge. So a positive charge is going to be removed, and then we're going to have negative charge. So this will increase the negative charge. Okay? So that's the first thing that will happen. Another thing, an amino group is going to be acetylated, and this acetylation is going to cause the charge to become less positive. So the carboxyl group, what will happen? It will be deprotonated. So we're going to remove a proton and it's become negatively charged. The amino group is going to become acetylated, and this acetylation is just going to decrease its positive charge, and it will become less positive. Then we're going to have an amino sugar that is, or like a polysaccharide that is sulfated. And by sulfated, what happens is we're going to add a sulfur group. And when we add a sulfur group, look at it, it's SO3 minus. So this minus is going to be there, so it's going to be negatively charged. So we're going to have, first of all, we remove the proton from the carboxyl group, so it's already negative. We acetylated any amino acid or any amino group we saw, we acetylated it. Awesome, guys, from the name, N-acetyl glucosamine. So we acetylated the amine group, okay? So it became less positive, and then we will add a sulfate. And from the name, guys, like heparan sulfate, dermatan sulfate, we add a sulfate, and this sulfate is going to increase the negative charge. Is it clear? So this is how it's negatively charged. Okay. Slay. See, guys, it's not hard. It's easy. صح? Okay, slay. Wait, guys, I need to just check one thing. Oops. Wait. Okay. So it's gonna be less negative. Let me try. Hello. Can you hear me?
Yes.
Okay, slay. طيب. تمام. Now, okay. So we talked about, wait, before that, we talked about the structure. So again, GAGs are highly negative. Why they're negative, we explained why they're negative. We said they're viscous, right? And we said they're made up of an amino sugar, an acid, and then like an acidic sugar with an acylated amino sugar. Clear? Clear. Now, they're highly negatively charged, and this is something we talked about. We said why. So because they're highly negatively charged, they're slippery or they're viscous, all right? So this slippery, since they're slippery, they're really good because it will help in the joints. So the glycosaminoglycans, what do they do? First of all, since they're slippery and since they're all negatively charged and they basically repulse each other and it's slippery, the negative charge will attract water. Why? How will it attract water? So we always know that negatives attract positive, okay? And what is an ion that we have in our body in abundance? Sodium. So what happens is the negatively charged glycosaminoglycans is going to attract the positively charged sodium, okay? And a rule that you guys have to have in your head forever, like forever, because you're going to take it in like different diseases. Sodium, wherever sodium goes, water follows. Water loves sodium. So if the sodium goes out, water will go out. If the sodium is attracted to negatively, like to the negative charge of the glycosaminoglycans, the water will be attracted to the GAGs. Okay, so when water will, since they're already slippery, so they're already like repulsing each other, and we have water. So when the compression happens, the water is just gonna go out. Okay, and whatever is inside is the what is it called? شو اسمه, the glucosaminoglycans going to like repulse each other. It's not gonna be fully compression, okay? And water can stay in here and it's going to become like more like it's not as forceful, something I know better, okay? So this skeleton is walking, the compression. Okay, so look at the skeleton as this person is walking, all right? You can see how the water is going to be squeezed out. They'll try to squeeze it out. You see, like the water will be squeezed out, and the glycosaminoglycans will try, like they're going to be pushed together. And since they're going to be pushed together, okay, they're not going to, because they're all negatively charged, they're not going to collapse, relax. There's going to be like some repulsion in between. So this will prevent the joint from prevent the two bones from collapsing into each other. All right? And then the water is going to just come back in when we relax. Tamam? Is it clear? So this compression, so when we say compression, we don't really mean compression. It's just like the two joints are compressed. The synovial fluid is compressed in between them. But it's not going to cause it's not going to be, remember guys, when we talked about condensation, we said when condensation happens, for the bone to happen, the water is going to leave, but they're going to meet together. But in here, in this thing, they won't, because the glycosaminoglycans, they're negatively charged and they're repelling each other. There are forces, so it will be so close together and they'll be compressed, but they'll never collide and be like, there'll be no space. Do you get me? Is this clear? Guys, please interact. So خلاص, it's clear?
Yes.
Okay, so gags are the cause of the resilience of synovial fluid and vitreous humor. So the synovial fluid, where is it found? In your joints. And the vitreous humor is the thing that makes up our eye. So you guys are going to take HNS in second year and you're going to take like the anatomy of the eye. But it's the thing that makes the eye like a globe and it makes it to be like full and like this is the vitreous humor. Okay? Now let's talk about the different types of glycosaminoglycans. Now, for the different types of glycosaminoglycans, we have 5 different ones that we're going to talk about today. Hyaluronic acid, dermatan sulfate, chondroitin sulfate, heparin and heparin sulfate, and keratin sulfate. All right? Now let's start with hyaluronic acid. Now, hyaluronic acid, it does not have a sulfate. All right? And it's not covalently attached to a protein. Yani it's not a proteoglycan. Okay? It's not a proteoglycan because we said it's glucosaminoglycans, like we said, no, they're usually bound to proteins, but in here, it's not covalently attached to a protein, okay? Now, let's look at the structure of hyaluronic acid. طبعا you don't need to know the structure, as in you don't need to know like how they look, like the rings, but you need to know what is it made up of. So hyaluronic acid is made up of glucuronic acid or glucuronate with an acetylglucosamine, and there's no sulfate, okay? So glucuronic acid, and acetylglucosamine make up hyaluronic acid. So it's unsulfated and it's not covalently attached to a protein. And we're going to later on talk about how like they're usually attached to a core protein forming proteoglycans, okay? So hyaluronic acid specifically is not covalently attached to a protein, okay? And guys, girls, I'm pretty sure you know how hyaluronic acid is amazing for the skin and how it's really good because it gives this basically you know, like the hyaluronic acid that you add to your skin, so basically it gives you like moisture. So hyaluronic acids, they're polymers, okay, and they're large. and they displace a large volume of water, making them good lubricators and shock absorbers in the joints. So hyaluronic acid, what do we mean by this? Hyaluronic acid are usually they're found in the joints, okay, like in the synovial fluid. And because they displace a large volume of water, so they'll displace the water, but they'll prevent it from compressing. They're going to be there, so they're good lubricators, okay? So they're going to lubricate, and they're good shock absorbers. So if we have like something going to the, let's say like a sudden movement, you're suddenly this is your knee, okay, like it's like this, so you're suddenly flexing your knee like this, so it's a good shock absorber. It's not going to cause them to collapse. It's going to be in here in the middle, and it's going to like kind of absorb the shock of the sudden movement, okay? And it's a good lubricator. It will keep them lubricated, okay? Is this clear? And
Yes.
it's usually found in synovial fluid, in the articular cartilage, skin, vitreous humor, ECM, okay?
Yep.
Tamam? Okay. Now these sugars, usually they're made in the cytoplasm. So they're made up in the cytoplasm of the cell, and then they diffuse to the plasma membrane for like to complete the synthesis. So these sugars, as in glycuronic acid and N-acetyl glucosamine, those are usually where are they synthesized in the cytoplasm. And then what will happen is they will diffuse to the plasma membrane where the hyaluronic synthesis happens. After they're synthesized in the cell membrane, they're going to be secreted into the ECM, unmodified. And we say unmodified, what do we mean? We're not going to add a sulfate because it's unsulfated, okay? And it's not going to be covalently attached to a protein. So this is the structure that will happen. So glucuronate or glucuronic acid and N-acetyl glucosamine is going to come together. They're going to be formed in the cytosol. They will diffuse to the plasma membrane where they will form hyaluronic acid. After hyaluronic acid is formed, it's just going to be secreted into the extracellular matrix. No modification will happen. It's not going to be sulfated. It's going to nothing else will happen. Okay? So this is hyaluronic acid is kind of like unique with that. And again, it's a good lubricator and it's a good shock absorber. Next. Then we're going to have chondroitin sulfate. Now, chondroitin sulfate is the most abundant GAG. So it's the most abundant. If anyone asks you what's the most abundant GAG, chondroitin sulfate, okay? And it's really, really, really important in cartilage. And now, by the way, people who have like they have problems in their joints, they usually take chondroitin sulfate as a supplement because they think it will help them. And it does, because usually chondroitin sulfate is found in huge amounts in the cartilage, bone, heart valves, everywhere. Okay? Now, what is chondroitin sulfate made of? It's made up of glucuronic acid with N-acetyl galactosamine. Okay, so hyaluronic acid is made up of glucuronic acid with N-acetyl glucose, but chondroitin sulfate is made up of glucuronic acid with N-acetyl galactosamine. Okay, just the most important thing again is just it's the most abundant and it's found in huge amounts in the cartilage. Now, chondroitin sulfate is not like hyaluronic acid. It does covalently bond to protein to form proteoglycans. Okay, so the only one that does not bind to proteins to form proteoglycans is hyaluronic acid. Tamam? Tamam. Now, another kind is dermatan sulfate. Dermatan sulfate is the same structure as chondroitin sulfate. The only difference is بدل glucuronic acid, instead of glucuronic acid, we have iduronic acid. Okay? So again, chondroitin is made up of glucuronic acid with N-acetyl galactosamine, so galactose. Dermatan sulfate is made up of iduronic acid or iduronate with N-acetyl galactosamine. Okay? So up till now, only hyaluronic acid is made up of glucosamine, and it's with what? It's with glucuronic acid. Okay? The rest are made up of N-acetyl galactosamine, so chondroitin sulfate and dermatan sulfate, galactosamine with, for chondroitin, so chondroitin is with G. Guys, you know how like in the DNA, how we have AT with and CG? So that's how you remember. Chondroitin is with C, G, glucuronic acid, CG. And it's not like, it's not related to DNA, but like, Anna, for me in my head, C with G, reminds me of DNA. You get me? Anyways, chondroitin sulfate, glucuronic acid. Dermatan sulfate, on the other hand, iduronic acid. Okay? Now, moving on, we have keratan sulfate. Keratan sulfate is unique. Why is it unique? Because it doesn't have an acid. We don't have la glucuronic acid, wala we have iduronic acid. What do we have instead? Galactose. Okay? So we're going to have galactose, and this galactose is going to be with an acetyl glucosamine, because we're not going to have two galactoses. Like, common sense. So galactose and acetyl glucosamine. Okay? So now we have chondroitin sulfate, dermatan sulfate. They have an acetyl galactosamine. Hyaluronic acid and keratan sulfate and acetyl glucosamine. What is the difference between keratan sulfate and hyaluronic acid? Keratan sulfate won't even have, like, it's not going to have an uronic acid. It's not going to have iduronic acid or glucuronic acid. Instead, it will have galactose. Okay, and it's easy to remember it, guys. Like, khalas, we have an acetyl glucosamine, so it's gonna since it doesn't have an acid, it's gonna have galactose, the opposite of glucose. Okay, it's not actually the opposite, but you get what I mean. Tamam? Now, keratin sulfate is found in the connective tissue, the cornea, and the bone. And it's important to know the cornea, and the cornea is in the eye. Okay. Now, in cartilage, it's aggregated with chondroitin sulfate. So we said no, keratin sulfate is found in cartilage. It's going to be aggregated to the chondroitin sulfate. Tamam? And it's covalently bound to protein to form proteoglycans. So all of them will be covalently bound to proteins to form proteoglycans, except for what? For hyaluronic acid. Tamam? So هلا guys, عندنا نحن, if you think of it, we have two exceptions. The first exception is hyaluronic acid is not in hyaluronic acid, it's not sulfated, and it's not bound to it's not covalently bound to proteins. Okay, this is for hyaluronic acid. The other exceptions is keratan sulfate does not have uronic acids, it has galactose. Okay, is everything clear by now? Yani guys, if I ask you about these, will you remember them?
Inshallah.
Did I make them easier, or are they still hard? Do you want me to repeat anything? It's clear. Okay. Tamam. So again, hyaluronic acid is unsulfated, does not bind to proteoglycans. It's made up of N-acetyl glucosamine with glucuronate. Tamam? Chondroitin sulfate and hyaluronic acid, it's a good shock absorber, good lubricant. What else? And also, guys, from the name hyaluronic acid, it does not have sulfate in the name. So that's why it's unsulfated. Okay? Then we have chondroitin sulfate and dermatan sulfate. Both of them are made up of N-acetyl galactosamine, either with glucuronic acid or iduronic acid. Okay? And what's the most abundant? Chondroitin sulfate. Tamam? Keratin sulfate, dermatan sulfate, we said iduronic acid, and that's all you need to know. And badal the glucuronic acid, it's iduronic with an acetyl galactosamine. Keratin sulfate, it's special. Why is it special? Because we don't have an acid or an acid sugar. We have the sugar itself, which is galactose. Okay, so galactose with an acetyl what? Glucosamine, because it's not going to be galactose again. Okay, it's like, now moving on, we have heparan sulfate. Now, heparan sulfate contains higher acidated glucosamine than heparan. That is something that we'll talk about later. And it's aslan, guys, if you look at it, it's, never mind. Anyways, and it's found in association, it's found in association with proteoglycans. So we have something called heparan sulfate proteoglycans in basement membrane. So the heparan sulfate, what will it do? It will bind to proteoglycans, forming SPG. This SPG is found in abundance in the basement membrane. Tamam? Now let's look at the structure. The structure is a bit different. It's okay, we have the glucuronate. This is something we know. Okay, but we have N-sulfo-D-glucosamine. And we said it's more acylated, and I don't think you guys need to know this, like N-sulfo-D-glucosamine, but you know it, like, in case, okay? So everything else is N-acetyl glucosamine or N-acetyl galactosamine, but heparan sulfate is special because it's N-sulfoglucosamine with a D, okay? So heparan sulfate is usually it binds covalently to proteins, forming heparan sulfate proteoglycans that are found where? In basement membranes, okay? Actually, heparan sulfate will bind to proteoglycans, yani heparan sulfate plus proteoglycans, okay? Which are basically what a protein plus whatever else like we took before. Is this clear?
Yes.
Okay. Should I move on?
Yep.
Everyone? Guys, it's clear for everyone? Tamam. Now we're comparing, we said here and it is higher acetylated glucosamine than heparin. Now what is heparin? Guys, have you heard heparin before this lecture? Have you ever heard of heparin? Because
Yeah.
it's a really famous, it's a really famous drug. So heparin is a drug that is usually used as an anticoagulant. And when we say anticoagulant, it prevents the coagulation of blood. So in our, like, if someone is injured or something, the blood is gonna coagulate. Sometimes people have problems in their blood where their blood highly is coagulable, like it forms clot, like it keeps on coagulating and forming clots, and it might be really bad. So that's why they give them anticoagulants, which an example of an anticoagulant is heparin. And heparin itself is found naturally in our body in mast cells. And mast cells, I don't know if you guys know what a mast cell is. Do you know what a mast cell is?
Yeah, we do.
صح, you took and yeah, you took
HLS with
yes, yeah,
FND.
true. So a mast cell is the cell that usually releases the granules when we have an allergic reaction, or when we have, like, you know how مثلا you like someone whoever eats a peanut and then having anaphylaxis. Why does he have this? Because the mast cell is going to release histamine, and the histamine is going to be released. One of the things that mast cells can release is heparin, okay? The heparin that we make in our body. So heparin is an intracellular granule of mast cells lining the arteries of lungs, liver, and skin. So you just need to know that heparin is basically something that is made in the mast cells, and it releases it. Okay, and the mast cells are usually found in lungs, liver, and skin, whatever. Now, heparin is more sulfated than heparan sulfate. And it's kind of funny because heparan sulfate has sulfate in the and heparan sulfate has sulfate in the name, but heparin doesn't have sulfate. So kind of it's ironic. So heparin is more sulfated, heparan sulfate is more acylated. Okay? This is the difference in like structure. Now, again, they're saying that heparin is an injectable anticoagulant. That's clinically, like if we make heparin, it's usually, it works as an anticoagulant. But in vivo, and in vivo means in our body, like the mast cells, they release heparin. It's usually a defense against invading bacteria and foreign substances. That's so mast cells, when they release them. So when mast cells is part of our immune system, they're not only active in like in hypersensitivity reactions, or when you have like a reaction to like something you're allergic to. It can also help in fighting bacteria and foreign substances like fungi and whatever. Okay, so again, heparan sulfate is more acylated than heparin, while heparin is more sulfated. Even though, so when you look at the options, when you see sulfate beside the name, just know that it's more acylated. While when you don't see a sulfate, it's more sulfated. Okay, I know it's confusing, but like, what can I do? Is it clear?
Yes.
Okay. I know you guys are tired. Wallah ma kun ha. How are we feeling? Are you guys okay? Is it a lot?
Yeah.
But do you feel like you understood it?
Yeah, it's okay. It's easy, just it's too much of content.
Yeah, I get you. That's medicine, sadly. Okay. يلا, moving on. خلاص نحن هلا in the last part, and then we're going to answer a couple of questions, and I'll see you guys إذا كنتم مركزين معي ولا لا. Anyways, now proteoglycans. So proteoglycans. So we talked about carbohydrates. We talked about glucosaminoglycans. Now we're going to talk about proteoglycans. So basically, we kept saying that the glycosaminoglycans, they usually bind to a protein, and when they bind to a protein, they'll be called proteoglycans. Okay, so in here, proteoglycans, they will act as tissue organizers. This is just know that proteoglycans equal tissue organizers. That's all you need to know. Tamam? And you need to know this, the structure. So the structure, let's look at the structure. So we have a glucosaminoglycan here, and then we have here a core protein. Okay, but the thing that binds the glycosaminoglycan with the core protein is called a tetrasaccharide linker. Tetrasaccharide linker means it's made up of sugar, because saccharide means sugar. So we have 4 sugars, okay, 4 sugars that will bind to the core protein. And these sugars usually bind to the protein via or through a serine residue. Serine is an amino acid. You know serine. So serine is an amino acid. So this serine is gonna, so we have protein, we have glycosaminoglycan, okay, protein, and then in between we're gonna have, I don't know how to hold this, okay, in between we're gonna have the tetrasaccharide linker. Now this tetrasaccharide linker is 4 different saccharides, okay? So we have we have here, this is the glucuronate acid, galactose, and xylose. I don't know if you guys need to know these, but yani, galactose, xylose, glucuronate or glucuronic acid. So glucuronic acid, galactose, xylose. Those 4, the tetrasaccharide linkers, I don't think you guys need to know them. Just know if you can memorize these, it's good. But I don't think they'll ask you, صراحة. Like, I'm not sure. I don't think they'll be like, oh, what does the tetrasaccharide linker look like? Or they might, wallah. Just know it's gal in the middle, xylose, and then glucuronic acid, Z. Okay? Anyways, so this is the tetrasaccharide like bridge. How will it bind to the protein? Through a serine, okay? That's all you need to know. So we have glycosaminoglycan, tetrasaccharide bridge. We'll have a serine in here. This serine, this is how the serine will bind. So tetrasaccharide with protein through a serine, okay? Tamam? Is this clear? So you only need to know proteoglycans, tissue organizers. They are made up of glycosaminoglycan plus core protein. How are the glycosaminoglycan with the protein? Through a tetrasaccharide bridge. This tetrasaccharide bridge will bind to the core protein through a serine residue. Tamam? Clear?
Yes.
Are there any questions? Well, guys, if you have any questions, tell me. Was it
That's
clear?
pretty clear.
Okay. For everyone? Okay. Now, proteoglycans, we have just like functions. We just have like a couple of examples. So let's say, like here, they're giving you heparan sulfate. Like if heparan sulfate was, so okay, so it will bind to a protein. So heparan sulfate binding to, شو اسمه, it will bind to signaling molecules, okay? So look in here. Let's look in here, okay? Wait 1 second. Okay. So this is heparan sulfate. This thing is a heparan sulfate, and it has something called NS domain. So NS domain, they're just saying, you know, it's something that's highly sulfated. So we have a lot of sulfate in this area. So this NS domain has a lot of sulfate. Now what will happen? This heparan sulfate, it will bind to a molecule, okay? Usually what happens, this sulfate, they will bind to a signaling molecule or to a molecule, and they will alter their function. So let's say this molecule's like the normal, this molecule, its function is to, I don't know, do whatever, okay? When it binds to heparan sulfate, so let's say this is heparan sulfate. When it binds to heparan sulfate, the function of this will be altered. It will be changed, okay? So usually we have something, so an example is we have something in our body called antithrombin, okay? Antithrombin, from the name, it prevents formation of thrombus, antithrombin, okay? But for it to be activated, okay, what happens is that the antithrombin will go and bind to a heparan sulfate. And when it binds to that heparan sulfate, it will kind of activate it, okay? It will kind of activate it. So this is the antithrombin. It binds to the heparan sulfate, and then it will kind of like put it there, okay? And then this heparan sulfate, this like antithrombin, it will be exposed, and it will allow the blood clotting factor XA to bind to the antithrombin, preventing the clotting from happening. Okay, I know I said alter their function. Alter their function as in I mean like molecules sometimes they exist in our body, and like okay, so you know how okay, so you know how in uni we have fire hoses that just exist there, but when will they be functional? When we have like a fire, right? So antithrombin is there in the blood like all the time, okay? But when it's there in the blood, that doesn't mean it will prevent the formation of a clot by just existing there. No, what happens is it will bind to the heparan sulfate. Oops. It will bind to the heparan sulfate for it to be kind of activated, so it will alter their function, okay? So it will be activated, and now once it's activated, the factor XA will bind to it and it will prevent clotting. Is this clear? You just need to know, heparan sulfate alters, it binds signaling molecules to alter their function. That's it. So not specifically heparan sulfate, proteoglycans in general, okay? Is this clear? But is the example clear? Yes. خلاص, should I move on? Okay. Another thing they do is it binds to enzymes. So it can bind to enzymes. Once it binds to the enzyme, it will kind of like, so you see here lipoprotein lipase. Those lipoprotein lipase, they're just circulating around in the blood and they're unactivated. Once they bind to the basically heparan sulfate in the extracellular matrix, okay, they will be activated, or they will be just kind of placed in one place, and this will help them to break down the triglycerides that are walking with. Like, because think of it that way. If something is walking, okay, in the blood, everything is going together, right? If the lipoprotein lipase is moving with the cholesterol, will it be able to break down the cholesterol or the triglyceride? No. But if it's basically anchored somewhere and then the cholesterol will pass by, it will bind to it and it will break it down. Tamam? Because it's harder for it to like while walking. No, it needs to be like placed in a place. It attaches to the extracellular matrix that has the proteoglycan, and it helps in the function. Tamam? So what does it do? It will, so in general, proteoglycans, they will either bind to an enzyme to stabilize it and make it work, do its job, or it will bind to signaling molecules and alter their function and makes them do their function. Tamam? Is this clear? Should I move on? Yes, slay. Now, last but not least, like the last thing that we need to talk about are the lysosomal diseases, lysosomal storage diseases. And I know it's weird because, okay, we're talking about glucose, we're talking about glycosaminoglycans. Like, what do you mean lysosomal storage diseases? Now, basically, what breaks down the membrane-associated glycosaminoglycans? Basically, lysosomal enzymes. So if we want to break down the GAGs, what do? We bring lysosomal enzymes. And if we have problems in the lysosomal enzymes, or if we have defects in the lysosomal enzymes, we want to be able to break down the GAGs, and they will accumulate, and this will result in the formation of lysosomal storage diseases. Okay, these diseases are called mucopolysaccharides. No, wait, mucopolysaccharidoses. Okay, and from the name polysaccharidosis, because we have polysaccharides, and muco is just there for the vibes. I don't know why there's muco, but mucopolysaccharidosis or lysosomal storage diseases. Okay, now in here we have so many different diseases, but the doctor looked at eye cell disease, Hunter and Hurler syndrome. Okay, now in all of these diseases, GAGs will accumulate in the lysosomes of the affected cells. So the GAGs, what will happen? The GAGs are going to accumulate in the lysosome. Why? Because the lysosomal enzymes are defected, or like they have a problem, or they're whatever. For what they cannot break down the GAGs, so they're just gonna accumulate and result in the formation of lysosomal storage disease. Tamam? Now, the disorders are all of these disorders, Hunter, like all of the lysosomal storage diseases, except like Hurler and eye cell disease, they are autosomal recessive. Except for Hunter, it's X-linked recessive. And do you guys know what X-linked means? يعني هلا you can keep in your mind and all of them are recessive except for Hunter, it's X-linked. So all of them recessive, Hunter is X-linked. Do you know what X-linked means? Did you take this in
Yes,
genetics?
it's on the X chromosome. So, for example, if it's X-linked, then it's going to be more dominant in a guy.
Exactly. So X-linked means basically إنه it's more dominant in guys. Basically, guys are more likely to inherit it. تمام? Okay. Moving on. These disorders, Hurler, Hunter, eye cell disease, they're usually characterized by severe psychomotor impairment and premature death. So whoever has these diseases are going to probably die early on. Most of them are not even going to reach their 20s. Some of them can reach 60s or 40s, but that's in very mild cases when they have mild forms of the disease. But most of them like really die early on. Tamam? And they cause psychomotor impairment, and by psychomotor impairment we means they cause problems in their brain. So they're probably going to have issues like mental retardation. They're going to be very aggressive. Okay, now we're going to talk more about the diseases in batch way, but for now let's look at here. So this is the normal breakdown of the GAGs. This is the functional one. What happens usually, first of all, we're going to have endocytosis of the GAGs. Okay, usually the GAGs are found in the ECM. Okay, so it's easy. So the cytoplasm is gonna go in, the cell membrane is gonna form a vesicle, and we're going to have the GAG inside the vesicle. This is phagocytosis or endocytosis. Okay. Specifically, like this is a kind of phagocytosis, specifically endocytosis. So we're taking it in. Then the lysosomes, okay, so these are here are the GAGs and the vesicles, and then the lysosomes are going to fuse with this vesicle, forming phagolysosome. And in this phagolysosome, this lysosome usually has all of the enzymes that are going to basically break down the GAGs, which are called acid hydrolysis. Why is that hard to say? Acid hydrolysis, okay? So these acid hydrolases are going to usually break down the GAGs. And so what happens is the polysaccharide chain will break down. So these enzymes will come, they'll break down the polysaccharide chain. And there's something that happens last on, first off on degradation. So last on, first off degradation. What does that mean? So when we are forming the glycosaminoglycans, the first molecule, okay, when you're forming the glycosaminoglycans, so the first, second, third, blah, 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 the last molecule is the first one to be degraded because they're going to start from backwards, if you get me. يعني مثلا, let's say we have glucose, xylose, whatever, okay? Xylose is the first one that's gonna go, and then glucose, and then you get me? So it's just last on, first off. I don't even know if that's important, but it was mentioned. Last but not least, the enzymes needed are glycosidases and sulfatases. It makes sense. We have glucuronic acid, we have glucose, we have galactose. So we're going to need glycosidases to break it down. And we have sulfates. We said we have to add a sulfate group to make it more negatively charged. So it makes sense and a sulfatase is going to remove it. Okay? Clear? Actually, the glycosidase is there to break down the glucose, the glucose, like the sugars. The acid hydrolases are there to break down the glucuronic acid and the iduronic acid. Tamam? So these are the enzymes that are needed. Is it clear? It's an easy process. Like if you think of it, it's just vesicle. Then from the vesicle, it's going to basically bind to the lysosome. Lysosome is going to break it down. And if the lysosome is not there, if they have defects in the enzymes, then it's just gonna it will form this vesicle, but the enzyme, but whatever is inside the vesicle is not gonna be broken down. And that's how we have the diseases that we talked about. Tamam? Clear? Do I move on? Does anyone have any questions? Tara, this is very high yield, guys. This is so important. Later on in your board exams, they're literally gonna be really important. They love asking about these questions. So is it clear? Hello?
Yes, it's clear.
So, do I move on? Everyone? Yes, okay, so now let's talk about eye cell disease specifically. Now, eye cell disease, the problem is in mannose-6-phosphate, okay? Now, mannose-6-phosphate, why is it important? It's important because it's there. It's like a protein tag. Guys, okay, let's say Anna, I have a bunch of tasks that I need to do, okay? And you need to put which tasks are the most important. So you kind of let's say put an asterisk on this task or put it first or whatever. So you tag this task or you tag this thing. So mannose-6-phosphate is a molecule that usually tags the proteins and shows, when it tags the proteins, this means it is there for degradation. Okay? So this mannose-6-phosphate, usually it tags the proteins and shows them that these are destined for basically degradation. But if this mannose-6-phosphate is not there, then nothing will be tagged, then nothing's going to be degraded. Then what will happen? They'll just accumulate and accumulate and accumulate and accumulate. So this is what happens in eye cell disease. Mannose-6-phosphate is not there. All of these proteins that are supposed to be dead or are supposed to be degraded by lysosomal enzymes are not degraded, and they just accumulate. Now, all of these are going to cause these symptoms, which are basically skeletal abnormalities. So anywhere we have lysosomes, and we have basically, anywhere we have lysosomes in these, we're going to have this. So basically, and we have the glycosaminoglycans, that's where this will happen. So they'll have skeletal abnormalities. They'll have restricted joint movement. It makes sense because we said in the joint, the cartilage, the synovial fluid, all of these contain gags. But the joint movement is going to be affected. We're going to have coarse facial features. And we say coarse facial features, we mean their faces are not going to be, they're going to have specific facial features, and it's literally in here. You see how these have these facial features where they're you can see that there's something not normal about this. You get me? But this is because the glycosaminoglycans, we said they're found in our skin, they're found in our body. So basically they're going to accumulate, and then we're going to have this kind of facial features. Severe psychomotor impairment, we said most of them are going to have problems in their brain, mental retardation, they can be very aggressive and so on. And all of this is due to the accumulation of the glycosaminoglycans. Okay? Usually we said they don't really live like long, so they usually die by the age of 8 years. They can't live more than 8 years. That's for eye cell disease. So eye cell disease, the main issue is mannose 6 phosphate. We don't have mannose 6 phosphate, or it's not functional, or I don't know what the problem is, but mannose 6 phosphate is affected. It has a defect. And because mannose 6 phosphate is not working, it's not phosphorylated, we're not having this phosphorylation, we're not having this tag, we're not tagging the protein that needs to be degraded, we're going to have accumulation of whatever protein that is not functional anymore. Tamam? Leading to the formation of eye cell disease. Now, in here, we're talking about Hurler's disease. We have Hurler and Hunter. Okay, they're kind of the same thing, with a little bit of differences. Now we're going to talk about it. But مثلا شفتوا هون we said إنه extracellular glycosaminoglycans are not degraded, resulting in this soft tissue of the face, resulting in the coarse facial features. تمام? Now, Hurler and Hunter syndrome. Hurler and Hunter syndrome, they're kind of the same because they're kind of the same. Why? Because we have the same glycosaminoglycans accumulated. So we're going to have a problem in the degradation of dermatan sulfate and heparan sulfate. So both of these, we have a problem in the degradation of dermatan and heparan sulfate. Okay? Both of them, it's affected. But the difference is, the enzymes that are affected are different. So in Hunter syndrome, which is MPS 2, okay, mucopolysaccharidosis 2, okay, no comment. What happens is we're going to have a problem in iduronate sulfatase, okay? So iduronate sulfatase is in Hunter syndrome. And how do we differentiate Hunter syndrome and Hurler syndrome? غير الانزيم, like clinically, by the problem, by one very specific thing. Guys, in Hurler syndrome, we're going to have corneal clouding. Corneal clouding, as you can see it here. Do you see how the cornea is clouded with whatever, like this is probably, remember how we said, no, one of them, اللي هو basically dermatan sulfate. So, yeah, dermatan sulfate is found in the cornea. Do you remember that? It was حتى bolded the cornea. Here, the cornea is clouded. We're going to have corneal clouding. Why? Because dermatan sulfate makes up the cornea and it's not broken down, so it's going to accumulate, forming corneal clouding. But in Hurler syndrome, we're going to have corneal clouding. In Hunter, we're not going to have corneal clouding. And how do you remember this? Guys, Hunter, he's a hunter. When you hunt, you go for hunting, you need your eyes, صح? So you're going to need the eye to look into the pistol and to like shoot and stuff like that. In Hunter syndrome, the eye is spared. We don't have corneal clouding, and we're going to have all the different things الباقيين اللي هن mental retardation, physical deformity, all of these things. But in a clinical scenario, when you see corneal clouding, it's directly Hurler, because a hunter needs his eye. Okay? And I'm not sure, guys, if you need to know the enzymes or not. صراحة, like depending on your lecture, if Dr. Abdul Jabbar told you need to, just memorize them. If he didn't say you have to, then just don't. Tamam? Now, they will affect the liver, the spleen. So we're going to have hepatomegaly. What does hepatomegaly mean? The liver is big. So when they do physical exam, they're going to realize that the liver is bigger than usual. Okay? Splenomegaly. Megaly means big. So we have increased size of the spleen. So when they're palpating the stomach, when they're feeling for the organs, they're going to feel like there's an increased organ. And we're going to have basically mental retardation. We're going to have deformities in the extracellular matrix. All of these make sense because think of the initial structure. Dermatan sulfate, heparan sulfate, where are they found? In the extracellular matrix. So they're going to affect, we're having deformities there because they're accumulating. And guys, what's accumulating is the things that are already like wasted, like dead. Like نحن, when we tag something for degradation, why do we tag it? Because خلص, like it should die, it's bad, it's not working anymore or whatever. But when these accumulate, it's bad. تمام? We're going to have mental retardation. We talked about this. Oligosaccharides in urine, except of excretion of fragments before the block. I don't know what that means. But we're going to have oligosaccharides in urine. Why? Because we have a lot of dermatan sulfide, a lot of heparan sulfate, a lot of things that are being there, okay? They're being, what is it called? Accumulated. Tamam? Is this clear? So if I say corneal clouding, what do you think of? Hurler. When I say no corneal clouding, Hunter. Okay? It's like what is being like affected? Heparan and dermatan sulfate. Next. This is just, you know, like a revision. I don't even know if you guys need to know Sanfilipino A and Morchio A, like I have zero idea. But you have to know Hurler and Hunter. And if you guys look, Hurler and Hunter, it's both of them are idorino, okay? So like if there was a bunch of enzymes, you can look for idorino and kind of like see. Hurler, we have an L in the middle. And the L in here is kind of in the middle. It divides the alpha from the iduronidase. Here, the L is at the beginning, so it definitely is not that. And in here, we have sulfatase. Here, we don't. Okay? So Hurler, well, like guys, Anna, for me, like I'll be honest with you, I'm never gonna memorize this. Like I'm not gonna know the name, but look at the structure. Like it's gonna be an MCQ. But look for the L. If the L is sandwiched between two things, then it's Hurler. It's the enzyme for Hurler. If the L is at the beginning, then it's for Hunter. If we have sulfatase other than the iduronidase, that's Hunter. Okay? Those are just ways of memorizing whatever this is, because I don't know if you need to know the enzyme. Maybe you do. But if you do, that's how I would personally memorize it. L in the middle, we have an L here, so this is Hurler. So alpha L irodinase, or the one that does not have sulfatase is for Hurler. Okay? Clear? Yalla guys, now we're going to have a bunch of questions. So questions time. طبعا the attendance like decreased a lot. It's funny, but yeah. Let's start. What are these isomers called, guys?
Enantiomers.
Yes, they are enantiomers. So basically they are mirror image. So it's like you looking at yourself. Enantiomers. Okay? Yalla. Which of the following sugars is not a reducing sugar? Remember the exception that we said at the beginning? We said most of monosaccharides and disaccharides are reducing except for
Sucrose.
did you say glucose?
Sucrose.
D?
Yeah.
Do you guys agree? I need everyone to answer محبتك. But thank you, Humira. I'm so sad. Like, I'm sorry, it sounds mean. I didn't mean that. I just mean I want everyone to like say something.
No, but I'm just doubtful about it.
You're being doubtful about it? No, it's actually the right answer.
D.
Yeah, it is
Yeah.
D. It's sucrose. So basically, everything, like not everything, but like most disaccharides and monosaccharides are reducing sugars except for sucrose. Now, why is it important to regulate the blood glucose levels between 4 to 6, whatever this unit is, especially in diabetics?
B.
Do you guys agree? Everyone? Okay. صح.
Also,
wanna-
can you please show the past two questions real quickly again?
What?
Could you show the previous two questions really quickly again?
Yeah, sure.
Okay.
Do you just want to see them, or like I'm gonna
Yeah.
send the slides for you guys anyways.
Mm-hmm.
Okay, yeah.
Thank you.
Let's go back. Okay, yalla, next. We need to match the following gags with their characteristics. Yalla, let's start. Okay, so these are the different gags that we're going to have, and these are the characteristics. So let's read the characteristics and then we'll read these, because we need to like, or you know what? Let's go like that. We'll start with heparan sulfate, okay? 1, is it found in connective tissue, cornea, and bone? We have cornea. So do you guys think it's heparan sulfate? Hello?
No.
Okay, we have 1 no. Does everyone think it's a no? No. You the guys answer. Oh, actually, we're only 3 in here. Anyways, okay. So yes, it's not one. It's the most sulfated and it acts as an anticoagulant.
No.
Okay, it's not. It's present in cartilage, bone, and heart valves.
No.
It's a component of the basement membrane and it has the HSPGs.
Yes.
Slay. Okay. Now, chondroitin sulfate. Okay, not covalently bound to proteins present in synovial fluid. No, that's hyaluronic acid. So, chondroitin sulfate. Do you think it's found in connective tissue, cornea, and bone? No. Chondroitin
No.
sulfate is not found in the cornea, right? طيب, is it the most sulfated and it acts as an anticoagulant?
No.
طيب, is it present in cartilage, bone, and heart valves?
Yeah.
Yeah, so that's the answer. Slay. Now, keratin sulfate. We said keratin sulfate is the one that is found in.
Yeah.
Yeah, exactly. So keratin sulfate is the one that is found in the cornea. تمام? Last but not least, heparin. It acts as an anticoagulant and it's the most sulfate. It makes sense. Yalla, now, which glycosaminoglycan is the most abundant in the body and binds to the collagen and cartilage? Yalla, which one is the most abundant?
Hyaluronic acid.
Is it hyaluronic or chondroitin?
Chondroitin.
So you guys agree C or B?
C.
Okay. It's C. Chondroitin sulfate. Do you remember how we said chondroitin sulfate is the one that's the most common, and it's found in almost in cartilage of all of the joints, and people who have like joint problems, they take it as a supplement. Okay. Which of the following glycosaminoglycans is unique for being synthesized in the plasma membrane and secreted into the extracellular matrix without any covalent modifications? So we don't add
C.
anything. C. Does everyone agree? Do you think it's hyaluronic acid? The boys C.
Because it's the only one that does not have any covalent modifications.
Exactly. It does not have any, it's unsulfated. We don't have covalent bonding. So hyaluronic acid is the only one that doesn't have any covalent modifications after it's done. Okay. Now, a 12-month-old female infant exhibits severe developmental delay with associated macrocephaly, dysmorphic facies, hypertonia, and hepatosplenomegaly. Clouding of the corneas is not evident. A pebbly ivory-colored lesion is present over the infant's back. The activity of iduronate sulfatase in the plasma is not detectable. These symptoms are indicative of which of the type of the mucopolysaccharidosis.
B.
We have 2 hints. B. صح. We have, first of all, no clouding of the cornea. Second of all, the one with the sulfatase is there. So we said no sulfatase is for Hunter, right? Iduronate sulfatase is Hunter. So صح, guys, it is B. Now, you're examining a 2-year-old child presenting with disproportionate short trunk dwarfism. Additional physical signs are coarse facial features, corneal clouding, and hepatosplenomegaly. You suspect the child is suffering from a lysosomal storage disease and order a test for alpha hydrogenase activity and find that it's severely impaired. Which of the following would you expect to find at elevated levels in fibroblasts from a skin biopsy? So what is accumulated? Chondroitin sulfate? No. Heparin sulfate? Do you think it's correct? Hyaluronate, keratin sulfate. What do you guys think? First of all, what's your diagnosis? What is this syndrome? We have corneal clouding, we have hepatosplenomegaly, we have
Hurler's syndrome.
exactly, and you see he ordered a test for alpha hydrogenase. It doesn't have a sulfate, and it usually has an L, this one they did not include it, so it's Hurler. So what's gonna accumulate? Heparan and dermatan sulfate. That's it, guys. Thank you so much for joining.
Thank you.
Do you guys have any questions?
No, thank you.